Hello dear colleagues and welcome to Civil Curious channel. In this video we are going to talk about concrete columns completely. You know, let me write our topics. What our topic is. Our topic is about concrete columns. As you know, column is an element in reinforced concrete beam, reinforced concrete structures, that is endure axial forces. Okay, let's get started. Generally, we have two kind of concrete columns. The first one is short columns, and the second one is long columns. Short columns are used in our structures. Are used in our structures. And long columns are not common, but there are. Okay, first of all, I'm going to show a section of concrete column in the ultimate state for you. Let me draw that. This is the shape of section of columns, in the ultimate state. And these are AS, that I call it tensile reinforcement, and these are A'(S), that we call it compressive reinforcement, and I'm gonna show you now what is happening in a strain of reinforcement in the ultimate state. Let me address that this section is for ultimate state of concrete column. Okay, we have here a strain of reinforcement of tensile reinforcement, and we have here a strain of compressive reinforcement. Okay, and we have here a strain of concrete in the ultimate state, or we CU is short letter of crushing concrete. You know that in the ultimate state, in the final state, our concrete will be crushed due to that moment. This is a strain. This is the strain, and now I'm gonna draw the stress. I apologize for drawing like this. I'm gonna show that with this array, because in the ultimate state our stress is not equal, is not identical, but for simplifying that, we have to show that identical to continue our calculation. and this is the yield stress for our reinforcement, tensile reinforcement, and this is the stress for our compressive reinforcement, you know. And we have the stress for concrete. The value is 0.85 of F prime C. That shows the stress of concrete, or concrete stress, you know. And why we chose 0.85 for concrete? This is because of simplifying of calculation that codes, concrete codes offers 0.85% of concrete stress, you know. And now I'm going to tell you our column how much could endure axial force, you know. We want to calculate the maximum load on concrete column, you know. We know that the let me change the marker. We know that the pure axial load of column, know that the pure axial load of column is equal to, I don't have enough space, I want to write that in left, is the load, or is the concrete load plus the plus all of rebar's load, plus all of rebar's load. I mean both tensile and compressive reinforcement, you know. This is the ultimate pure axial load of column. And how can we make it math, you know? How can I write it? I write that P0, that shows the pure axial load of a column, that is equal to concrete load, which is 0.85 F prime C times the area of concrete in the ultimate state. That I will show that what is the area of column in the ultimate state, plus load of rebars, which are AS plus A prime S times the yield stress of reinforcement, you know, in the ultimate state, you know. And I'm gonna continue. What are these numbers? What are these loads, you know, and how can I simplify that in calculation? I can write that like this. We know that in the ultimate state, both of concrete and compressive reinforcement are in compression, you know. These are both are in compression. And how can I write this? You know, I can write that the pure ultimate load of column that we call it P0 is equal to 0.85 F prime C, that shows the concrete tension times the growth area minus the area of steel or reinforcement, plus the area of reinforcement times the yield stress of reinforcement, which we have here. The area of reinforcement is equal to A prime AS, that is tensile reinforcement, plus A prime S, which are compressive reinforcement. This is the simplified equation, and I'm gonna explain that for you. Uh, as I said before, this is A prime. This is the area of concrete. The area of concrete is equal to the total area of our column, that we call it the growth area minus the area of a steel. That was our method. As you can see, this is the whole equation that shows a concrete column will endure axial load, because it's included with concrete and steel, and these two terms are the ultimate load that both can endure. Okay, let me continue for you. For general works, for general designing, we have the I just want to make a view for you. F prime C, or the ultimate stress of concrete, is equal to 25 megapascal. We use in our design generally, and for steels we have the F prime or yield stress as 400 megapascal. These numbers are general and are used in common reinforcement rebars. Okay, and now I'm gonna calculate the ultimate strength of concrete column. Let me write this topic. We're gonna calculate the maximum compressive compressive strength of column, especially nominal, maximum nominal compressive strength of column. Okay, or P N max, maximum nominal axial force of column. We're gonna calculate that from the ACI code 318. We have that the maximum nominal load of column is equal to 0.80% of the P0, that we call it up. This is for columns with a closed tie. The maximum load is equal to 0.80%. The ACI decreased 20% of P0. you know. And for circle columns, we have the maximum nominal strength as 0.85% of P0, you know. This equation is for spiral actually spiral tie or circle columns, you know. Be careful that don't uh, don't make identical the maximum. These are completely different. Don't make a mistake. P0 is not identical, is not uh, identical of maximum of nominal strength, you know, because we decreased 20% and we decreased 15%. You know, these are not the same. Don't make a mistake. And now I'm gonna show you what is the maximum load that every column could endure in design of structures. You know, we have two load for column. One load is uh, the strength of column, that we call it P0 or nominal P. This is the load that every column has into that, could endure it. And we have another axial load or action that is applied to our column. These are completely different, and codes I'm going to show you how codes are calculating these items, you know. Let me change the marker. We show the applying load. Let me close this area. We show the applying load to column as PU. You know, this is applying load. To concrete columns, and this is the nominal strength, and this is the strength of column. You know, and concrete codes tell us these PU should be less than these number that we call it phi times the nominal P. You know, this phi is the coefficient that decrease the nominal strength. You know, and for sorry, let me close this area already. I'm going to continue on top of the page. Okay, and for columns with closed tie, we have phi, which is equal to 0.65, and for spiral columns, we have phi as 0.75. You know, this shows us, you know, this is show us for spiral column we have more safety factor, and the spiral columns are more reliable for concrete codes. This is real. This is truth. You know, this is for, let me write that, close tie, and this is for spiral columns. You know, let me continue, everybody. We told the main thing for concrete column until here, and now I'm gonna calculate the maximum tensile. You all know that concrete couldn't endure tensile force. You know, this is the reason. And in the low tensile forces, the concrete will be cracked, and we remove them in calculation. This is the reason. Let me write that for you. I'm going to write that we removed the term of concrete area because concrete could not endure tensile force. You know, because of this, we remove the concrete term, and the maximum nominal strength of concrete column is the area of steel times the yield stress of steel. You know, that was the strength of column. We just calculate both strengths of column in tension and compression, everybody. And I'm gonna, if you all or agree, solve two equation, two or three problem of concrete columns for you. Okay, and we have some topic like calculating of the center of plastic for columns. This is our topic, you know, that which is really complete. And calculating and the topic of columns in moment, you know, two-way moment, one-way moment, when our column is subjected to both moment and axial force. This is a really interesting topic, really interesting topic, you know. And the columns in two-way moment that I've said before, these are a great topic. But before everything, we just talked about the strengths in tensile and compressive, and I'm gonna solve two problems. Let's get started. I'm going to, let me close this area. I'm gonna draw a column here. I was not a good painter. Never. Okay, which has reinforcement like this. For reinforcement in every side. You know, okay, these are the longitudinal rebars. Now I'm going to draw the tie for this column. As you can see, our column has closed tie that I said that the maximum nominal strength will be 0.80% of P0. There is not clear enough cover in this side. I apologize for such a drawing for you of you. This is tie. Okay. Let me change the marker. Our longitudinal rebars are 12 of feature 20. The size of steel is 20 millimeters, you know, and our closed tie is feature 10 millimeter, which is used every 20 millimeters or every 200 millimeters. And both our column is is a square. Both sides are 500 millimeters. Every number that I use in my problem is millimeter. You know, our unit weight. Millimeter is our unit. You know, we're gonna calculate these parameters that I taught just now. P0 and maximum nominal strength of column and the maximum nominal tensile of column, you know, and the proportion of tensile strength to compressive strength, that we call it Pn max divided by Pn T max divided by Pn max. The proportion of tensile strength to compressive strength. Okay, let's get started. First of all, let's calculate. Let me change the marker. Let me calculate the 0 P0 that we have that before. P0 is equal to, let me write the equation again to review that. P0 is equal to 0.85 F prime C. This is C. Sorry. Let me erase that, clean that. This is F prime C times the growth area minus the area of steel plus the area of steel times the yield stress of steel. You know, now let's calculate. P0 is equal to 0.85. We suppose I told you we suppose the F prime C or crushing strength of concrete 25 megapascal times 25 times the whole growth area of column. Our column is a square and both sides is 500 millimeters. So we have the area 500 to the power of 2 square meter of 500 minus the area of steel. All of our steel, we have 12 rebars which are 20 millimeters, you know, and the method is like this: minus 12 times P divided by 4. We're going to calculate the area of circle times 20 to the power of 2, you know, 20 square meter, you know, plus plus 12, you know, we're gonna calculate this term times P divided by 4 times 20 to the power of 2 times the yield stress of rebars. Our steel, I told you, the yield stress of rebar is, we suppose that to be 400 megapascal. You know, now I'm gonna close this equation, and our answer will is in terms of Newton, and when I multiply that to 10 to the power of minus 3, our equation will be kilonewton. I calculate that, and the answer is 786.83 kilonewton. This is our answer. This maximum point that our column could endure, you know. And now I'm gonna calculate the maximum nominal. P0 is not nominal. The maximum nominal strength of column in compression. We call it Pn maximum. I told you that the value of Pn max for closed tie or square column is 0.80% of P0, which is equal to Pn maximum is equal to 0.8 times 7786.83, which is equal to, I calculate that, 6229.47 kilonewton. This is another answer. Okay, and Let me calculate the third term, you know, PNT maximum, the maximum tensile strength of concrete column. Let me write that. PNT maximum is equal to, we had that equation, which is a area of steels times the yield stress of steels. Okay, I'm gonna continue like this. Is equal to, we have 12 steels time P divided by 4 time 20 is the power of 2 square meter of 20 times the yield stress of steel, which is 400 megapascal, times 10 to the power of -3, because we're gonna have our answer in unit of kilonewton, which is equal to, I calculate that the answer is 157.96 kilonewton. You know, let me close that. Yeah, calculate this, and for the last term we have this term, we have this equation. We're gonna calculate the PNT maximum divided by PN maximum, which is 157.96 divided by 6229 0.47. The answer is 0.24. You will see that the tensile strength of column is far from the compressive strength of column. The compressive strength of column is hardly greater than the tensile strength of column. You know, I think that was a useful problem that reviewed all of things that we have learned by now. And for you, I want to solve another problem to review all of things that we have learned. Okay. Now I hope you all don't be tired, and if you all feel like so, please drink a tea or coffee to have that enough energy. You know, let's get started. The second problem tell us we have a concrete column that in this column we have the maximum compressive strength 4 times greater than the maximum tensile strength, you know, which is actually natural, you know, and our concrete strength is 30 megapascal. We show that like this. Our concrete is C30. Okay. Sorry. Is C30, and the yield stress of our steel is 400. We have in the basic, we write that S 400. We show that like this when we want to say that the yield stress of reinforcement is 400. Okay, what the problem want us is that what is the percentage of steel in this column, or rho is equal to what? We want to calculate the percentage of steel in this column, and also we know that in this column we have a spiral tie. You know, our column is circle, or this is a circle column. Okay, let me solve this problem. Okay, as data of problem, we have that the maximum compressive strength of column is 4 times greater than maximum tensile strength of column. Okay, and we have the spiral type for column that the maximum nominal compressive strength of column will be equal to 0.85% of P0. Okay, and the maximum tensile strength of column is equal to area of all of steels times the yield stress of a steel. Okay, and as we reviewed before, the P0, is equal to for circular columns 0.85 F prime C times the growth area of column minus the area of steel plus the area of steel times the yield stress of a steel. This is the equation of P0. Actually P0 is the maximum load endurable for column without any eccentricity. Set that to your mind. P0 has no eccentricity. Okay. Okay, let me continue. We have here P0. I'm gonna write P0. Which is here. We have here maximum nominal is 85% of P0, and the P0 is 85% of F prime C times other. Okay, I'm gonna write like this. Be careful. 0.85 times 0.85 times F prime C is 30 times we don't know the gross area of our column. We don't know the dimension of our spiral column, so I have to write AG because I don't know that, minus the area of STO that we don't know that 2 plus 400. I don't know that the area of a steel, but I know that the yield stress of a steel, which is 400. you know, and this equation is 4 times greater than this equation, 4 times the area of steel, you know, times 400 illusters of steel, you know. And we can times this parameter to this parameter, you know, and uh, take that to other side. Take that to other side. We can calculate this parameter times a steel, and calculate this term and take these terms that have a steel to this term, to other side of equation. You know, we have that. Do that at home. I just want to write the what I've calculated. We have, the answer is, we have 21.675 Ag, you know, minus 21.655 of a steel plus 340 a steel. This is what I have in this side of our equation. You know, this is equal to 1,600 a steel, you know, and we can simply calculate the proportion of a steel to growth area of the gross area of our section, which is equal to, I calculate that the answer is 0.0169. This is the answer. And the when we want to calculate the proportion of steel to growth area of our section, we can multiply this answer times 100. How? Like this. We have rho that is equal to a steel divided by gross area times 100. This is the percentage of steel in our section. Rho is equal to 1.7%. Okay, I hope you all enjoyed this problem, everybody, and have enough view and comprehension of concrete column, the strengths of concrete column, you know. Now let me continue and solve another equation for you. I want another different equation. Sorry, I want to solve another different problem for you in this field. Okay, let's continue. Another problem tell us we have a concrete column which let me change the marker, which the maximum strength in comparison of column is 35 greater than the gross area of concrete. This is an interesting, actually beautiful problem. The P0 is equal to 35 Ag, the gross area of our concrete column. And we have the P and T maximum, the maximum tensile strength of our column as 1,400 kilonewton, you know, and we have the strength of concrete 35 megapascal. Our concrete is C35, and our steel are S400. Okay, and what the problem wants us is the dimension of our column. You know, the demand of problem is what is dimension of this column. This is the demand. Okay, let's solve this problem, everybody. We know that the P0 or maximum axial load without any eccentricity for column is 0.85. You know this equation very well now, everybody. I hope so. Times Ag minus the area of steel plus the area of steel times the yield stress of steel. This equation is according to ACI. I repeat that. Okay. And we have the P and T maximum, which is maximum tensile strength of column, is to be area of steel times the yield stress of steel. So from this equation we have the area of steel to be P and T maximum, the maximum tensile strength, divided by tensile yield stress of steel. Okay, from this equation let me solve the area of steel, which is the maximum tensile strength that the problem tells us. This is 1,400. This is 1,400, you know, times 10 cubic, 10 to the power of 3, or cubic meter. Okay, divided by yield stress, which is 400, and the answer is A steel is equal to 3,500 square millimeter. Okay, we have solved. We get the value of steel in this equation, in this problem, and we have here 35 Ag that problem told us. We have here 35 AG is equal to 0.85 times 35, which is the concrete strength, times AG. We don't know that. For calculating the dimension of column, at first we have to calculate the AG, the gross area, minus the area of steel, which is 3,500, plus 1,400 times cubic meter of 10, or 10 to the power of 3. Okay, this is a simple equation. You have to calculate this term for AG and transfer that to the other side, and then we actually could simply solve this equation and simply get the value of AG. Okay, I've solved that. I just write the answer we have here, because we don't have enough time to calculate that. 5.25 AG is equal to 129.5875, and the AG will be equal to 2468 33.3 square millimeters. Okay, we have just earned the value of AG in this equation, and for calculating the dimension, we know that let me add here, we have our column is a square. We have a square column, and the AG is one side of a square to the power of 2, or I'm gonna name that B. Square B is equal to AG, and B, or dimension of our column, is B2 is equal to AG, so B2 is equal to 246,833.3, and the value of dimension of our square column is 496.8 millimeter, which is approximately 495 millimeter. This is the dimension for our concrete column. Okay, I hope you all enjoyed this different problem. Okay, everybody, in this video I have told you the type for, let me review our lesson, today's lesson. Okay, at first in the first minutes of session, I told you the type of columns. There was short columns and long columns, and I introduced you the pure axial load of column, that was the strength of column strength of concrete in compression plus the strength of all of steels in tension, and I show you the value, and here I draw that, okay, and I explained the equation for you. You know, I explained completely for you what was the P0, the relation of P0, and the what is the maximum nominal strength of column for closed tie columns, and what is the maximum nominal strength for column for spiral tie. You know, I explained that for you, and I should tell you that the maximum load applying to column should be less than phi times the maximum nominal strength, you know, and continue. And I've solved 3 equations for you that I hope all of them to be useful for you. I believe that if you solve these problems and review these equations, you should be dominant on this topic. This is the first problem, this is the second, and this is the third problem. And I hope you all enjoyed this video. For the next session, I will share the topic of center of plastic for column, and the moment and the axial force applying to column, you know, and we will discuss about it, everybody. I hope you all enjoy it, everybody, and I want you all to not be tired and have that energy to review and to practice more and more. And if you like it, please subscribe the channel to motivate me to create more videos for you. Thank you very much.